Morning everybody. So today we're going to do a relatively short lesson. We're just going to be looking at, instead of differentiating today for variable acceleration, we're going to be looking at integrating to help us with variable acceleration questions. So the first thing to note is yesterday we found that if we differentiated a formula for displacement, it gave us the velocity. If we integrate both sides of this, and we integrate them with respect to time, and whenever you're doing these questions, time is always going to be the variable you're integrating with respect to. So I'm integrating this with respect to time. I signify that I'm integrating it with respect to time by writing dt at the end. And similarly, I'm going to integrate v with respect to time. So if I do those two things, this thing just goes back to being displacement again. Essentially, I'm undoing the differentiation by integrating again. And this side, I'm not going to do anything with for now. I'm just going to leave it as it is, dt. So in other words, if somebody, if the question gives you a formula which is in terms of velocity and it's a function of time, then I can integrate this with respect to time to find out what the displacement is. Similarly, if I have dv over dt, so I've differentiated velocity. If I differentiate velocity, I get acceleration. Can you guys just pause the video and just, after I finish saying this, can you do the same thing for acceleration just to get a formula for that in terms of integrals? Okay, so just pause the video and quickly do that. Okay, so hopefully this side you've just integrated to get dv dt with respect to dt, and that's that with respect to time, and this leaves me with velocity is equal to the integral of acceleration with respect to time. Okay, so those formulas are useful to know. It's just a reverse of what we did yesterday. However, the reason why I've gone through it is because hopefully by doing this, some of you are now saying to yourself, but sir, when I integrate things without limits, I should get some constants. Now, what I've written down here is absolutely fine. Yes, strictly speaking, you should have had a constant here and a constant here. However, because I know that there's a constant going to come out here, and I haven't done it yet, I can essentially combine those two. So what I've written isn't wrong. But thinking about, okay, well, when I integrate this, finally I should have a constant now, and you should. And so when we do questions, we don't want constants just lying around. We want real values because these are real life problems. And so the questions normally give you some starting conditions, and those starting conditions are going to be your limits of integration. So let's just have a look at an example of that. Okay, so here's the example we're going to do. Find the position s of a particle at time t, given that s equals 3 when time equals 0. In other words, it's not at the starting point, it's 3 whatevers away from the starting point. When I say starting point, I mean from O. And its velocity is given by v equals 5t minus 2. Okay, so what I'd like you guys to do is just have a quick think about what you might need to do first, and have a quick think about how you might use those initial conditions to answer the question fully. Pause the video, have a quick go, and then come back when you want to check what you've done. Okay, so hopefully you started by saying, well, s is equal to the integral of velocity with respect to time. Now, it's really important that you have velocity in terms of time. You must write it next to the equation what it is in terms of time, because if you're integrating with respect to time, if you've got stuff in here which isn't time, then that's not going to work. So for this question, velocity is 5t minus 2. And I'm doing that with respect to dt. I'm going to write s here because I'm going to use that in a minute because I'm going to substitute in. And so if I integrate this, I've got s is equal to, so I need to raise the power up and divide by it, raise the power up and divide by it, and I've got some constant that I don't yet know. Okay, so I've got s equals 5t squared minus, divided by 2, minus 2t plus c. Okay, so my initial conditions were that s equals 3 when time equals 0. Whenever it says time equals 0, you should be celebrating because it really, really helps. So the displacement is 3, and then I've got 5 times 0 squared over 2 minus 2 times 0 plus c. I've substituted in 0 for time, 3 for displacement, and hopefully you can see that that's going to be left with that c just has to be 3. Therefore, and you really must do this last line, s is equal to 5t squared over 2 minus 2t plus 3. Okay, so just one last thing to mention before I let you crack on with some exercises. Quite often they'll give you the initial conditions in terms of s is this when time is this or whatever else. The one way that they can do it without giving you explicit numbers is by saying things like after starting from rest. After starting from rest. At the origin, for instance. At the origin. So if you're starting from rest at the origin, so after starting, that implies at t equals 0 from rest. That means that the original velocity is 0, or let's put u, I suppose, for the initial velocity. And at the origin, that must mean the displacement was 0. So in other words, if they write the sentence as starting from rest at the origin, then in other words, at time equals 0, the initial velocity is 0 and the displacement 0. I think that's probably quite obvious, but just in case it caught anybody out, we've added that one in. So exercises for today, you've already got the sheets from yesterday and the answers, so it's exercise 1.3 again. Okay, so if you can do those 5 questions, question 3, 4, 7, 11 particularly need to get done. Question 14's seems a bit harder, but I think if you can get those 5 done, then that'll be enough for today, and I will see you tomorrow. Tomorrow we are moving on from kinematics. We're going to start talking about forces and motion, specifically Newton's laws of motion, so any of you that do physics will probably recognise quite a bit of that. Have a great day, and I'll see you guys tomorrow. Bye bye.